Hello, my name is Ruben Sansegundo and I'm going to present the ASenses framework for multi-sensorial perception. The presentation will have this index. First I will talk a little bit about the context, the main question I want to answer, some keywords, the framework and the main challenge, and some examples. Well, about the context, we have to say that currently the main research on perception is focused on how to simulate every sense with automatic system. In neuroscience, new research has provided the idea that the brain can change depending on the use of this brain. So we can define the brain plasticity or brain flexibility. So we can adapt the brain to do new tasks, and this adaptation can be done with enough training time. And the third aspect is the increment in multimodal interactive application fostered by video games company, where the main effort is focused on how to process and combine multimodal information from the user, but not so much effort has been done on how can we provide this information to the user, how the user perceives this information, or how can we increase the perception capability of the user. So the main question is, it is possible to perceive some information traditionally perceived through one sense through an alternative sense? My answer is yes, but probably it's necessary to invest some research effort on how to define a framework in order to organize this research. But I think the force is very active because there are a big amount of application. So if we talk about the signs, we have to talk about a hearing, a sense, touch, taste, smell, and if we analyze a little bit about the dimension we can deal with in the different sense, we can say that a hearing we have 1 + 1 dimension. It's true that we have 2 ears and we can estimate some localization problem, but these two signals are very correlated, so we should say that we have 1 + 1 dimension. In ASenses we have 3 dimension, and in a touch most of the time we have 2 dimension, but it's true that sometimes we have 3 dimension. And for a smell and a taste we have a finite number of possibilities. About the keywords, why the A? A comes from alternative sense. When one sense is overstimulated, we can look for an alternative sense in order to provide some information. For example, someone is listening music, some acoustic warning can be provided visually. Augmented sense because we can incorporate additional information, for example in the object we are looking at. Artificial because we can replace a damaged sense with an artificial sense. The person can perceive some acoustic information through an alternative sense, for example touch, smell, taste. And advanced sense because we can increase the human capabilities. We can provide human with an advanced sense, so we can increase the resolution, we can increase the range, we can increase the amount of information we can perceive. So in summary, we have augmented, artificial, advanced, alternative sense applied to hearing, signs, touch, taste, and smell. If we talk a little bit about the framework, generally if we want to translate the information coming from one sense in the information to stimulate another sense, we have to first to make signal capturing and processing, information extraction, and then the new information coding, representation, and finally we have to combine this new information with the normal perception through this alternative sense. What about the main challenge? But Well, in the first model, we have to improve the sensor devices for some sense, like the smell. We have to improve the processing algorithm, and we have to increase the information modeling. We should improve the algorithm to select the most important information depending on the context. We have to define how can we represent this information based on the brain plasticity, how the new information must be represented to be perceived through the alternative sense. And finally, we have to answer two main questions: how the new information must be combined with the normal perception through the alternative sense, and when or where the new information must be presented in order to avoid bothering the normal perception. This challenge must include research from different areas: engineering, neuroscience, and human modeling. Let's see a couple of examples: hearing and ASenses. Hello, my name is Rubén Sansegundo, and I'm going to present the demonstration hearing. In this demonstration, the system will visually represent acoustic event. The system will detect and localize acoustic event and represent them in a screen. This demo has a lot of application, like artificial hearing for the people, or it's an acoustic warning for the people, or people who is listening to the radio or some music, for example. The model diagram of the system consists of, first of all, a dummy with two microphones located in its ears. And from this microphone, the system performs a binaural acoustic recording. This recording will allow detecting acoustic events and localize them. When detecting an acoustic event, this event will be classified and in case of a speech, this speech will be recognized. This information will code and represent in a screen. The main characteristics of this system is the detection is based on energy levels, the localization is based on two binaural cues, the interaural time difference and the interaural level difference. The classification is performed using Haydn-Markov model using the ATK. This is the application toolkit for HTK. The coding and representation of this event are based on simple icon using the Microsoft Foundation classes of Windows. In the demo, we will see at the beginning of the process this bitmap. That means that the system is starting. During this starting, the hearing software loads the acoustic model and estimate the acoustic noise level. During the process, we can configure two main aspects of the system: is the sensibility and the priority. The sensibility is how sensible is the system to the acoustic event, and the priority is the priority of this program compared to other programs. In the demo, we will see something like that. In the screen, some icons represent an acoustic event. For example, we can represent a whistle music, some spoken expression like good afternoon, buenas tardes, and applause, and this icon will be localized. It depends on the acoustic source location. The main challenge to address in the future is to improve the signal processing technique for acoustic event detection, but also for localization. Special emphasis will be provided on binaural acoustic event classification and binaural speech recognition. Let's see the demo. Buenas tardes. Adiós. Hasta luego. Hello, my name is Ruben Sansegundo and I'm going to present the demonstration ASign. This demonstration has been developed by Jose Moreno and Arturo Romero as a project for the Digital Electronic System Laboratory supervised by myself. This system will provide audio description for test signs detected by video processing. The system will detect test signs and generate an acoustic spoken message explaining the test sign. Some possible application of this demo will be developing an artificial vision for blind people, an automatic warning generation when detecting test signs for absent-minded people, for example. The model diagram of the demo is composed by a video camera, high-definition video camera. Then we capture the video and we process the video, trying to localize the text in the image. This text will be passed through the optical character recognition system in order to provide a test sequence. This test sequence will be compared to different signs in order to generate the closest one. The closest one is explained with a text-to-speech synthesis model. The main characteristics of the system are the following. For video capturing, we use the video input library using the Hewlett-Packard webcam, high-definition webcam. For processing and processing the video and test localization, we use the OpenCV software. For optical character recognition, we use the Tessera software. For test sign selection, the Levenstein distance, and for text-to-speech synthesis, we use the Loquendo. In the demo, we will see a camera and we will see the image and the main image detected by the camera, and in the left bottom of the image we see a black-white image where we can see the test. This image will pass through the OCR in order to detect and recognize the test. The recognized test will appear at the left top part of the screen. At the same time, the system will provide a spoken message saying that the exit sign has been detected. Let's see the demo.
Salida de emergencia. Salida. Exit. Extintor.